All right, hello everyone. Welcome back. So today we're gonna begin section 16.1. This vector field and the conservative. Vector field. Okay, so number one. Vector field. A vector field on a region E and R3 is a vector function having the form f x, y, z. So this is a vector. So it is the a x, y, z, right? I plus b x, y, z, j plus c x, y, z, k. So this a lot of people prefer to write this as the A, B, C. Yeah, it's A, B, C. Yeah. Hopefully, most of you know that you can get to the point just by a vector from the origin. So there's the vector 1, 2, 3. No, sometimes the vector field is also called the force field. Simplest one, fx, y is equal to two component here, negative y, x. Now we can sketch this one. I'm just gonna sketch a few points here, and then the rest of them is just gonna use the GeoGebra to do the sketch. Okay, usually I would suggest that you get a table here, and then you can do the sketch on the table. Okay, so x, y, pick point 0, 1, something so I can sketch. The vector here is -1, 0. Okay, let's sketch this thing out. Right. So at the point 0, 1, we have a vector field -1, 0. What does that vector look like? -1, 0. I mean, the vector is going to go -1 in the direction of x. Yeah, here's what it looked like. Right? And then let's pick another point here. Like 2, 2. So you get an idea. -2, 2. Okay, so 2, 2. Yeah. This point. -2, 2. Well, most of you know how to sketch that thing, right? You just have to make a box and then you just draw the arrow as the diagonal line in that box. So this do this thing here. And 2, and then 2. So the vector is gonna be this vector right here. Let's say and when you connect all the vector together, you're gonna get a vector field. As for the vector field, it's just use GeoGebra, right? Negative y. And the other one is x. Oh, wow. Look at this thing here. Pretty nice, huh? Using GeoGebra, we see that the vector field is a rotational field or a rotational flow. Okay. For the three-dimensional, right? I'm not gonna do the hand sketch though because it's terrible. But then we can sketch it to see what it looked like using GeoGebra. So here come another example. When you do this, you got to switch. It got to be a 3D. Okay. GeoGebra, right? This only the vector field up to 2D though. Vector fields in 2D. As you go back here, the vector field in 3D. It's the same author. X, Y, Z. Okay. Look at this. It looked like it is the radiating. You can actually figure out the amount of fluid flow. That's pretty cool later. But it's just for you to get a visual of what is going on here in case the vector field is a velocity vector. 2. Let's move on to the conservative vector field. This is a very important concept in the later section. So here come some definition for you guys, a few definition. Our first definition is if f, x, y, z is a scalar function, in all three, just a scalar function, not a vector field, then it has a gradient vector. Well, you guys already know, right? There's the gradient vector here. fx, fy, fz. And I'm gonna put here f. Okay, so here come another definition. A vector field is said to be conservative. So this is the vector field, right? And it has a gradient vector field. A vector field is said to be conservative. On the region E in all three. If there exists a scalar function fx, y, z so that and most of you can guess, right? The vector field F is exactly the gradient vector field of the scalar function determined which vector field is conservative. For the partial derivative to be valid, they must satisfy the Clairaut theorem. You gotta remember this theorem in chapter 14. The second partial derivative, right? Fxy must equal to fyx. Right? Okay. So you just have to do the testing here. Right? Okay. F, right, is equal to, well, fx, fy, right? Well, is the fx and fy, are they some partial derivative of some function? We don't know, but then we can use the Clairaut theorem here. Test validity with Clairaut theorem. Oh, that's amazing. We have this theorem, huh? So we have to test it, taking the partial derivative with respect to y of fx. This is exactly fxy. Partial derivative with respect to y of xy squared. And with respect to y, what do we have? We have a 2xy. Do the same thing. Partial derivative of y with respect to x. X. Partial derivative with respect to x of fy. To xy. So yes, y square z square x. Okay. You actually have to run through 3 pairs, right? But then if one of them does not agree with each other, then you don't have to do the second pair. fxy equal fyx, fxz equal fzx, and one more, fyz equal fzy. Partial derivative with respect to y of fx. Partial derivative with respect to x of fy. Partial derivative with respect to y of x squared y. Partial derivative with respect to x of y squared z. So what do we have here? We have a x squared. Okay, try this one. xy equal fyx, fxz equal fzx, fyz equal fzy. Partial derivative of y of 1, partial derivative with respect to x of psi z 0 0. Good. Partial derivative with respect to z of 1, partial derivative with respect to x of y cosine z. Good. And then move to the last one. Partial derivative with respect to z of psi z. Partial derivative with respect to y of y cosine z. And then cosine z, yeah. 3 equality. So yes. Yes. F is conservative. This should be a fun one here. Example. If f is conservative, find a scalar function f so that the vector field f is the gradient vector of the scalar function. And here come your vector field here. Two x y x squared minus 3y squared. We can do this thing real quick. Partial derivative of y of fx there. That's 2x that partial derivative with respect to x of fy. Okay, good. Conservative. So there should be an s. There exists fxy. So how do we get fxy here? You just have to do the antiderivative here. So we're not. It doesn't matter where you begin, right? Fx is 2xy. Right? I'm gonna integrate both sides here. Integrate. Integral fx dx is integral 2xy dx. Right? Okay, so what do we have? We have a fxy. Right? You don't worry about the c, because if you move the c to the other one, it's going to get another c here. Integral with respect to x is going to be well, x squared y. Nah. Okay. So next step here is that, well, we're gonna use the info on fy equal to oh yeah, I forgot to do the plus c here. Plus c. However, this c here, because we take the derivative with respect to x, we treat y as the constant. So c is the function in terms of y. So this is going to be a gy. C is a function in terms of y because we treat y as a constant. So use info on fy equal x squared minus 3y squared. Okay, so we're going to use it. What does this mean? It's going to be a partial derivative with respect to y of f x y. This should equal to fy. So what does this mean? It's the partial derivative with respect to y. Fxy is the x squared y plus gy, right? And the fy is x squared minus 3y squared. Now what do we have here? We have a x squared plus g prime y is equal to x squared minus 3y squared. So what's this mean? G prime y is equal to minus 3y squared. And then integrate both sides. Integral g prime y dy integral minus 3y squared dy. So that means gy is, well, minus y to the 3 plus c. And then finally, fxy is x squared y plus now the gy, so minus y3 plus c. X squared y minus y3 plus c.